In 1977, a Soviet icebreaker called the Mikhail Samov was cutting through the Ross Sea when its sonar picked up something unusual. A structure on the ocean floor, beneath more than 400 meters of water, that had a regularity no geological formation should have. The crew logged it, reported it, and the report was classified. Nobody knows what it was. The file has never been made public. That is where this story begins. Not with what we know about Antarctica, but with what we are not allowed to know. Beneath the ice that covers the southernmost continent on Earth, there is a world that has been sealed from the surface for 30 million years. A world of mountains taller than the Alps, of lakes larger than Lake Erie, of rivers that flow in total darkness under 3 kilometers of ice, of geological formations that have never been touched by sunlight since the Eocene epoch. And the treaty that governs Antarctica, signed in 1959 and renewed repeatedly since, contains a clause that effectively prohibits any nation from extracting, drilling, or fully exploring what lies beneath that ice until at least 2048. 48 nations have signed it. None of them has publicly explained exactly why the moratorium exists, beyond the official answer of environmental protection. Tonight we are going to go beneath the ice. We are going to explore what the science actually tells us is down there, what the expeditions that have been allowed have found, and what the boundaries of the permitted knowledge are. And we are going to ask, calmly and carefully, whether the official explanation is the complete one. If you are new to the channel, subscribe now. Every week a new documentary designed to keep you company as you fall asleep, exploring the strangest and most hidden corners of Earth and the universe. Antarctica is the highest, driest, coldest, windiest and most isolated continent on Earth. It contains 90% of the world's fresh water, locked in ice sheets that in some places reach 4 kilometers in thickness. If that ice melted entirely, global sea levels would rise by approximately 60 meters, submerging every coastal city on the planet. The continent is larger than Europe, larger than the continental United States and Mexico combined. And yet, for most of human history, no one knew it existed. The sheer physical scale of the Antarctic ice sheet defeats any attempt to comprehend it through statistics alone. The numbers, 2.6 million cubic kilometers of ice, 4 kilometers of thickness at its deepest point, 90% of the world's fresh water, do not translate into anything the human mind can picture directly. What the numbers mean, in human terms, is that if you were to stand on the surface of the ice at the South Pole and drill straight down, you would pass through more than 3 kilometers of ice before reaching bedrock. At that depth, the ice is not the brittle, fracturing substance familiar from cold climates. It is a plastic material, deforming slowly under its own enormous weight, flowing outward toward the edges of the continent at rates of a few meters per year in the interior and several kilometers per year in the ice streams that discharge into the surrounding ocean. The first confirmed sightings of Antarctica occurred in 1820, within days of each other, by 3 separate expeditions from Russia, Britain, and the United States. The continent had been theorized for centuries before that, appearing on maps as Terra Australis Incognita, the unknown southern land, based on the philosophical assumption that a landmass must exist in the south to balance the landmasses of the north. But no human being had actually seen it until the 19th century, and no human being set foot on the interior of the continent until 1911, when Roald Amundsen reached the South Pole ahead of Robert Scott's ill-fated expedition. The wildlife of the Antarctic coastal zone is another aspect of the continent's story that contrasts sharply with its barren interior. The Southern Ocean that surrounds Antarctica is one of the most productive marine ecosystems on Earth, driven by the upwelling of nutrient-rich deep water along the Antarctic Convergence, the zone where cold Antarctic surface water meets the warmer waters of the subantarctic. That productivity supports vast populations of krill, the small shrimp-like crustaceans that form the base of the Southern Ocean food web, and through the krill, populations of whales, seals, penguins, and seabirds of extraordinary abundance. The coastlines of Antarctica during the summer are among the few places on Earth where wildlife exists in the kind of density that characterized most of the world's oceans and continents before human exploitation depleted them. The Antarctic Treaty of 1959 is one of the most remarkable international agreements ever signed. It was negotiated during the height of the Cold War, at a moment when the United States and the Soviet Union were engaged in a global competition for territorial and technological supremacy. Both nations had active research stations in Antarctica. Both had conducted extensive surveys of the continent. And both agreed, along with 10 other nations, to sign a treaty that declared Antarctica a continent devoted to peace and science, prohibited military activity, banned nuclear testing, and most significantly for our purposes tonight, suspended all territorial claims. The treaty did not say that no nation could own Antarctica. It said that existing territorial claims were frozen, that no new claims could be made, and that the scientific community had free access to the entire continent. 7 nations had already made territorial claims to portions of Antarctica, including Argentina, Chile, Australia, New Zealand, France, Norway, and the United Kingdom. Those claims were not cancelled by the treaty. They were simply put on hold indefinitely. The Protocol on Environmental Protection to the Antarctic Treaty, known as the Madrid Protocol, was added in 1991 and came into force in 1998. It designated Antarctica as a natural reserve devoted to peace and science, and it contained the clause that prohibits any activity related to mineral resources unless a new legal framework is agreed upon. That prohibition runs until 2048. After that date, it can be reviewed. The protocol does not say what happens after the review. It does not guarantee that the prohibition will be extended. Why 2048? The official answer is that the protocol needed a fixed review period to be politically viable. But several legal scholars who have studied the history of the treaty negotiations have pointed out that the 50-year period was chosen specifically to defer the question of Antarctic mineral resources to a future generation, a generation that would presumably have better technology, better environmental safeguards, and potentially better political frameworks for managing what could be the largest untapped reserve of minerals on Earth. The discovery of the subglacial lake network beneath Antarctica transformed the scientific understanding of what an ice sheet actually is. Before that discovery, the dominant model treated the Antarctic ice sheet as essentially a passive object, a mass of frozen water that accumulated over millions of years and that was slowly flowing toward the sea. The subglacial lake network revealed that the ice sheet is an active system, with liquid water moving beneath it in response to geothermal heat and pressure, lubricating the base of the ice and affecting the flow of ice streams in ways that feed back into the stability of the entire sheet. The discovery required a complete revision of ice sheet models, and the revised models have consistently produced higher estimates of potential sea level rise than the models they replaced. Because that is what lies beneath the Antarctic ice. The geological surveys conducted by the nations with Antarctic research stations, surveys that have been conducted for decades using seismic profiling, airborne radar, and satellite gravity measurements, have mapped a continent that contains enormous deposits of coal, iron ore, copper, gold, platinum, chromium, and hydrocarbons. The East Antarctic Craton, the ancient stable core of the continent, is geologically similar to regions of Africa and Australia that contain some of the richest mineral deposits on Earth. The Transantarctic Mountains, which divide the continent roughly in half, are a geological structure comparable to the Andes in their mineral potential. The world knows this. The nations that signed the treaty know this. And the decision to defer the question of mineral exploitation until 2048 was made with full knowledge of what was being deferred. The scientific infrastructure of Antarctica includes some of the most sophisticated instruments on Earth, placed there precisely because Antarctica's unique environment makes it the best location for those instruments. The South Pole Telescope, a large sub-millimeter wavelength telescope located at the geographic South Pole, is designed to study the cosmic microwave background radiation, the faint glow of the Big Bang that pervades the universe. The dry, cold air of the Antarctic plateau, almost entirely free of water vapor, provides ideal conditions for sub-millimeter astronomy that cannot be replicated anywhere else on Earth's surface. Similarly, neutrino detectors buried in the Antarctic ice sheet exploit the transparency of the deep ice to detect the passage of neutrinos, the almost massless particles produced in supernovae and other extreme cosmic events that travel through the Earth as if it were not there. But the minerals are only part of the story beneath the ice. The more scientifically extraordinary discovery of the last 30 years has been the subglacial lakes. Lake Vostok is the largest known subglacial lake on Earth. It lies beneath approximately 4 kilometers of ice at the Russian Vostok Station in East Antarctica, and it is approximately 250 kilometers long and 50 kilometers wide, making it roughly the size of Lake Ontario. The lake has been liquid for at least 15 million years, sealed beneath the ice by a combination of geothermal heat from below and the insulating pressure of the ice above. The water at the top of the lake is estimated to be at around -3 degrees Celsius, kept liquid by the pressure of the ice above it. The water at the bottom, near the geothermal sources, may be significantly warmer. The implications of Lake Vostok's existence are profound. A lake that has been liquid and isolated for 15 million years is a potential refuge for life forms that have been evolving in complete isolation since the Miocene epoch, when Antarctica was already largely ice-covered but the global climate was significantly warmer than today. Any organisms living in Lake Vostok would have been cut off from the rest of Earth's biosphere for longer than the entire history of the genus Homo. They would have had to survive in complete darkness, at near-freezing temperatures, with no input of organic matter from the surface, relying entirely on chemosynthesis, the ability to extract energy from chemical reactions rather than from sunlight. Russian scientists drilled into Lake Vostok in 2012, after more than 2 decades of technical preparation and international debate about the risk of contaminating the pristine lake environment. The drill reached the lake surface in February 2012, and a small amount of lake water was pushed up into the borehole by the pressure difference. Analysis of that water and of the ice that formed from it has produced some preliminary evidence of microbial DNA that does not match any known organism in international databases. The results have been disputed by some researchers who argue that the DNA could represent contamination from the drilling equipment, but the Russian team maintains that the precautions taken were sufficient to rule out contamination. The Antarctic Treaty's Article 4 is the piece of legal drafting that has kept the continent from becoming a site of territorial conflict for more than 60 years. The article states that nothing in the treaty shall be interpreted as a renunciation by any contracting party of previously asserted rights or claims to territorial sovereignty in Antarctica, and simultaneously states that no acts or activities taking place while the treaty is in force shall constitute a basis for asserting or denying any claim. That double negative, the refusal to confirm or deny any territorial claims, was the diplomatic formula that made the treaty possible. Every nation that signed could honestly tell its domestic audience that it had not given anything up. The price of that universally acceptable formula was a permanent legal ambiguity that leaves the underlying territorial question permanently unresolved. Lake Vostok is the largest, but it is not the only subglacial lake. Satellite gravity measurements and airborne radar surveys have identified more than 400 subglacial lakes across Antarctica, connected in some cases by subglacial rivers that flow beneath the ice for hundreds of kilometers. That network of subglacial waterways, which was completely unknown before the advent of modern remote sensing techniques, represents a hydrological system of extraordinary complexity operating in total isolation beneath the ice. The question of life beneath the Antarctic ice is not speculative. It is a question that the data has already begun to answer, though not yet definitively. The evidence for microbial life in the subglacial environment of Antarctica comes from multiple sources. Ice cores drilled from above Lake Vostok and other subglacial lakes contain accretion ice, ice that has frozen onto the bottom of the ice sheet from the lake water below, and that accretion ice contains biological material. DNA analysis of that material has identified genetic sequences consistent with bacteria, fungi, and other microorganisms, though as with the direct lake water samples, the question of contamination is difficult to completely rule out. The history of the dispute over the Antarctic Peninsula between Argentina, Chile, and the United Kingdom provides a window into the geopolitical tensions that the Antarctic Treaty was designed to suppress. The three nations have overlapping claims to the same sector of the continent, including the peninsula itself and the surrounding islands of the South Atlantic. The dispute became physically confrontational in 1952, when Argentine personnel fired live ammunition at a British survey party landing at Hope Bay. The incident was diplomatically resolved, but it demonstrated that territorial competition in Antarctica had the potential to produce genuine military conflict if left unmanaged. The Antarctic Treaty, negotiated 7 years later, was partly a direct response to that incident and to the broader realization that the Cold War competition between the superpowers, if extended to Antarctica, could turn a scientific and environmental issue into a military one. More convincingly, ice cores from other parts of Antarctica, drilled from ice that was not in contact with any known subglacial lake, also contain microbial DNA. Those organisms were presumably incorporated into the ice when it formed at the surface and have been preserved in a frozen state for hundreds of thousands of years. The ice of Antarctica is therefore a biological archive extending back further than any other continuous biological record on Earth, preserving genetic material from organisms that lived on the continent before the ice sheet reached its current thickness. The possibility that complex multicellular organisms, rather than just bacteria, might exist in the subglacial lakes has been raised by some researchers, though it is considered unlikely by most specialists. The argument is based on the existence of deep-sea hydrothermal vent communities in the modern ocean, which support rich ecosystems of worms, crustaceans, fish, and other complex organisms in complete darkness and at temperatures ranging from near freezing to several hundred degrees Celsius. If geothermal heat sources exist at the bottom of Antarctic subglacial lakes, and the evidence suggests that some do, then in principle the conditions for complex life could exist there. No one knows. The drilling technology required to reach the lake floor and retrieve samples without contaminating the environment is still being developed. The plans for further exploration of Lake Vostok and of the other subglacial lakes, including Lake Ellsworth in West Antarctica and Lake Whillans near the Ross Ice Shelf, are constrained both by technical limitations and by the international agreements that govern scientific activity in Antarctica. The question of what lives beneath the Antarctic ice may be one of the most important biological questions on Earth, and it remains unanswered. The atmospheric record preserved in the Antarctic ice cores has produced some of the most consequential scientific findings of the late 20th century. When researchers at the French-Soviet Vostok drilling project published their analysis of the Vostok ice core in 1987, they demonstrated for the first time that the concentration of carbon dioxide in the ancient atmosphere was closely correlated with temperature, rising and falling in synchrony with the glacial and interglacial cycles over the previous 420,000 years. That correlation, which has since been confirmed and extended by subsequent ice core studies, provided some of the strongest empirical support for the role of greenhouse gases in controlling global temperature, and it established the pre-industrial carbon dioxide concentration of approximately 280 parts per million as the baseline against which current concentrations of more than 420 parts per million are measured. The geothermal activity beneath the West Antarctic ice sheet adds another dimension to the mystery. A 2017 study by researchers at the University of Edinburgh identified a region of West Antarctica that may be sitting on one of the largest volcanic fields in the world, with up to 138 volcanic cones buried beneath the ice, some of which may be active. That discovery was made by analyzing radar data collected by aircraft flying over the ice, which revealed the distinctive shapes of volcanic structures beneath the ice. Whether any of those volcanoes are currently erupting, or releasing heat and gases at rates that affect the stability of the overlying ice, is not known. The history of human exploration of Antarctica's interior is a history of limits, both physical and political. The first overwintering expedition to the interior of Antarctica took place in 1898, when the Belgian Antarctic expedition became trapped in the ice of the Bellingshausen Sea and was forced to spend the winter aboard its ship. The psychological and physical toll of that winter, documented by the expedition's Dr. Frederick Cook, established that Antarctica's interior was not merely cold but actively hostile to human life in ways that went beyond temperature. The complete absence of sunlight during the polar night produced depression, psychosis, and physical deterioration in the crew that no amount of preparation could fully mitigate. Subsequent expeditions, culminating in the race to the South Pole between Amundsen and Scott in 1911 and 1912, pushed the limits of what human beings could endure on the surface of the continent. But the interior beneath the surface remained entirely unknown. The ice that covers the continent was understood to be thick, but the instruments to measure how thick, or to map what lay beneath it, did not exist until the development of airborne radar in the mid-20th century. The permafrost that underlies much of the Antarctic Peninsula and the subantarctic islands contains a biological archive that is separate from and complementary to the ice core record. Permafrost preserves organic material by keeping it frozen, and the organic material in Antarctic permafrost includes the remains of organisms that lived on the continent when it was warmer, including mosses, invertebrates, and the seeds of plants that no longer grow there. Analysis of that material has revealed that the vegetation of the Antarctic Peninsula was significantly richer and more extensive during warmer periods of the last million years than it is today, and that the transition from those warmer states to the present cold state happened rapidly enough to be geologically abrupt. That record of rapid transition is one of the data points that researchers cite when discussing the potential for rapid future changes in Antarctic ecosystems as the climate continues to warm. Operation High Jump, a large U.S. military expedition to Antarctica in 1946 and 1947, is one of the events most frequently cited by those who believe the official account of Antarctica conceals more than it reveals. The operation involved 13 ships, 33 aircraft, and 4,700 men, a scale of military deployment that is difficult to explain purely in terms of scientific research. The official purpose was to establish the feasibility of U.S. territorial claims and to train personnel for Arctic conditions. The unofficial purpose, suggested by some historians based on declassified documents from the period, was to survey the continent systematically using aerial photography and to assess its military and strategic potential. Rear Admiral Richard Byrd, who commanded the operation, gave a brief interview to a Chilean newspaper after the expedition's premature conclusion in which he reportedly made statements about Antarctica containing unknown territories and about flying objects that could travel from pole to pole at great speed. Those statements, if accurately reported, have been used by conspiracy theorists to support claims about secret Nazi bases and alien technology hidden beneath the Antarctic ice. Those claims are not supported by any credible evidence. But the interview, and the circumstances of Operation High Jump's premature conclusion after only 8 weeks of a planned 8-month mission, do raise legitimate questions about what the expedition encountered and what it found. The logistics of Antarctic research represent one of the most demanding and expensive scientific operations on Earth. Supplying a single inland research station requires a chain of air and ground transport that begins at coastal stations accessible by ship, continues through intermediate depots established on the ice, and ends with aircraft specially modified for operations at extreme altitude and cold. The fuel required to heat the stations and power the equipment must be transported from the coasts to the interior, a journey that requires either specially equipped tracked vehicles or aircraft. The carbon footprint of Antarctic research is, paradoxically, one of the largest per researcher of any scientific activity, because the remoteness and hostility of the environment require enormous energy inputs simply to keep people alive and equipment functioning. What is documented is that the aerial survey of Antarctica conducted during and after Operation High Jump produced the most detailed map of the continent that had ever been made, that significant portions of that map were classified for decades, and that the systematic aerial photography revealed geological features beneath the ice that were not publicly described until much later. The scientific instruments that have revealed the most about what lies beneath the Antarctic ice are not the drilling rigs that laboriously bore through kilometers of frozen water. They are the aircraft. Since the 1970s, a series of airborne surveys have used ice-penetrating radar to map the topography of the bedrock beneath the Antarctic ice sheet. That bedrock topography, which has been progressively refined through successive survey campaigns, reveals a continent whose surface, if the ice were removed, would look nothing like the flat white expanse we see in satellite images. Beneath the ice there are deep basins, some of them below sea level, that would fill with seawater if the ice were removed. There are mountain ranges that rival the Himalayas in height. There are vast plateaus and canyon systems carved by ancient rivers that flowed when Antarctica was a forested, temperate continent more than 30 million years ago. The most dramatic single feature revealed by the subglacial topography surveys is the Gambert-Sev mountain range, a mountain chain in the interior of East Antarctica that is comparable in size to the Alps. The Gambert-Sev mountains were completely unknown to geologists until the 1950s, when Soviet seismic surveys first detected their presence beneath the ice. They have never been seen by human eyes. They are buried under several kilometers of ice and are as inaccessible as the surface of another planet. And yet the radar surveys have mapped them in enough detail to reveal a landscape of jagged peaks and deep valleys that must have been spectacular when they stood above the surface of the Earth tens of millions of years ago, before the ice covered them. The subglacial topography also reveals something that has significant implications for the future of global sea level. Much of the West Antarctic ice sheet sits on bedrock that is below sea level, in deep basins that open to the ocean through submarine channels. That configuration, known as a marine ice sheet, is inherently unstable in a warming ocean because warmer ocean water can access the base of the ice sheet through those channels and melt it from below. The rate at which that process is occurring, and the rate at which it could accelerate, is one of the most important and most uncertain questions in climate science. The deep drilling projects that have retrieved the oldest Antarctic ice cores are among the most technically demanding scientific undertakings on Earth. The European Project for Ice Coring in Antarctica, or EPICA, drilled cores at 2 locations in East Antarctica that reached ice deposited more than 800,000 years ago, extending the continuous climate record back through 8 glacial cycles. The drilling required years of work at stations where temperatures outside the drill building regularly fell below -40 degrees Celsius, using drill fluid specially formulated to remain liquid at those temperatures and to prevent the borehole from closing under the pressure of the surrounding ice. The cores themselves, cylinders of ice 3.2 meters long and approximately 10 centimeters in diameter, were transported in insulated containers to laboratories in Europe for analysis, where researchers spent years extracting and analyzing the ancient air bubbles trapped within them. The geological history preserved in the ice itself is another source of extraordinary scientific information. Ice cores drilled at sites across Antarctica have retrieved ice that is up to 2.7 million years old, providing a continuous record of the Earth's atmosphere, temperature, and volcanic activity extending back to the Pleistocene. Those ice cores contain bubbles of ancient air, trapped when the ice formed at the surface and compressed as the ice was buried under successive layers of snowfall. Analyzing the gas composition of those bubbles allows scientists to measure the concentration of carbon dioxide, methane, and other greenhouse gases in the atmosphere at the time the ice formed, creating a direct physical record of past climates that no other archive can provide. The ice of Antarctica has also preserved a record of cosmic events. Micrometeorites, tiny fragments of extraterrestrial material that constantly rain down on Earth from space, accumulate on the surface of the Antarctic ice sheet and are concentrated at certain locations where the ice flows converge and the overlying snowfall is minimal. Those locations, called blue ice areas, have been systematically searched by meteorite hunters for decades and have yielded tens of thousands of extraterrestrial samples, making Antarctica the source of the majority of the world's meteorite collection. Among those samples are pieces of the Moon, fragments of Mars ejected by ancient impacts, and primitive chondritic meteorites that preserve material from the earliest period of the solar system, more than 4.5 billion years ago. The political geography of Antarctica is as strange as its physical geography. 7 nations claim sovereignty over sectors of the continent: Argentina, Chile, Australia, France, Norway, New Zealand, and the United Kingdom. Those claims are all based on either geographic proximity, historical exploration, or the principle of sector theory, by which nations claim all territory between specified meridians of longitude extending from their own coastlines to the South Pole. The claims overlap in several cases, most notably the competing claims of Argentina, Chile, and the United Kingdom to the Antarctic Peninsula and the surrounding islands, which have been a source of diplomatic tension and occasional confrontation for decades. The Antarctic Treaty suspended those claims without resolving them. The claimant nations still consider their claims valid. The non-claimant signatories, including the United States and Russia, consider the question of territorial sovereignty in Antarctica to be unresolved and deliberately unresolvable under the current treaty framework. That ambiguity was built into the treaty intentionally, because any attempt to resolve the territorial question in 1959 would have made the treaty impossible to negotiate. The practical consequence of that legal ambiguity is that Antarctica exists in a kind of international legal limbo. It is not a sovereign territory of any nation. It is not a global commons in the legal sense of the term. It is a place governed by a treaty that explicitly defers the hardest questions and that requires consensus among its signatories to amend. And since consensus among 48 nations on anything related to mineral rights, territorial sovereignty, or military access is essentially impossible, the current legal framework is self-perpetuating. It continues by default, because no alternative framework can achieve the consensus required to replace it. China has been conducting increasingly intensive scientific activity in Antarctica since the 1980s, and has now established 5 research stations on the continent, more than almost any other nation. Chinese scientists have been particularly active in the subglacial lake research and in the geological surveys of East Antarctica. The official position of China is that it supports the Antarctic Treaty System and has no territorial ambitions in Antarctica. The scale of Chinese investment in Antarctic infrastructure, which includes an icebreaker fleet and a network of stations across the continent, suggests a level of interest in Antarctica's future that goes beyond pure science. Russia has maintained Vostok Station, one of the most remote permanently inhabited places on Earth, for decades, despite the extraordinary logistical difficulty and expense of supplying a station at an altitude of 3,400 meters in the interior of the continent, in a place where temperatures regularly reach -60 degrees Celsius and lower. Vostok Station exists because it sits directly above Lake Vostok. The scientific and strategic value of access to that lake is the reason Russia has maintained a presence there at enormous cost. The international scientific collaboration that characterizes Antarctic research is itself one of the most remarkable features of the continent's story. Scientists from nations that are geopolitical rivals in virtually every other context work together on Antarctic research projects, share data, share stations, and publish jointly in ways that would be politically inconceivable in any other domain. That scientific collaboration is not an accident. It is one of the explicit goals of the Antarctic Treaty, which was designed in part on the model of the International Geophysical Year of 1957 to 1958, a globally coordinated scientific initiative that demonstrated that Cold War rivals could cooperate productively in the pursuit of scientific knowledge, even when they were unable to cooperate on anything else. The Antarctic scientific community has become a proof of concept for international scientific collaboration that its founders probably did not anticipate would last as long as it has. The ozone hole above Antarctica is perhaps the most globally visible consequence of human activity in the region, and its discovery in 1985 is a cautionary tale about the gap between scientific knowledge and political action that is relevant to many contemporary environmental challenges. British Antarctic Survey scientist Jonathan Farman and his colleagues published measurements showing that the ozone layer above Antarctica was depleted by more than 30% compared with measurements from 2 decades earlier. The finding was initially doubted because satellite data had not flagged the depletion, a fact that turned out to be because the satellite data processing algorithm had been programmed to treat such extreme values as errors and discard them. When the satellite data was reprocessed without that filter, it confirmed and extended Farman's ground-based measurements. The scientific and political response to the ozone hole, which led to the Montreal Protocol of 1987 and the subsequent gradual recovery of the ozone layer, is frequently cited as a model for how international environmental agreements can work. The Antarctic ozone hole was the test case that demonstrated the model was viable. The question that the science raises but does not answer is whether there is something beneath the Antarctic ice that no current theory fully explains. The most discussed anomaly is what has been called the Wilkes Land crater. In 2006, researchers analyzing NASA satellite gravity data identified a gravitational anomaly in the subglacial geology of Wilkes Land in East Antarctica, a region of unusually dense material beneath the ice covering an area roughly comparable to the Ohio impact crater on the Moon. The anomaly is consistent with a large impact crater, possibly the largest on Earth, dating to approximately 250 million years ago, which would place it at the Permian-Triassic boundary, the moment of the Great Permian extinction. If the Wilkes Land anomaly is an impact crater of that age and size, it could have been the direct trigger of the Permian mass extinction, the worst biological catastrophe in the history of complex life. That would make it one of the most consequential geological features on the planet. It would also mean that the evidence for one of the most important events in the history of life on Earth is buried beneath kilometers of Antarctic ice, inaccessible and unconfirmable with current technology. The anomaly remains controversial. Some geologists argue that the gravitational signature is more consistent with a region of unusually dense mantle rock than with an impact crater. The debate cannot be resolved without drilling through the ice to the bedrock and collecting samples, which is precisely what the current treaty framework makes practically impossible. The most important geological site on Earth may be permanently protected from the investigation that would confirm or refute its significance. The ice itself also behaves in ways that are not fully understood. The flow of the Antarctic ice sheet is driven by a combination of gravity, geothermal heat, and the lubrication provided by meltwater at the base of the ice. That flow is not uniform. Some portions of the ice sheet, called ice streams, flow much faster than the surrounding ice, and the behavior of those ice streams is one of the primary uncertainties in projections of future sea level rise. The West Antarctic ice sheet contains enough ice to raise global sea levels by approximately 5 meters if it were to collapse, and some researchers argue that the collapse of the West Antarctic ice sheet may already be underway, driven by the warming of the circumpolar deep water that is accessing the base of the ice sheet through submarine channels. Whether that collapse, if it is occurring, will unfold over centuries or over millennia is not known. The instruments that could answer that question with confidence do not yet exist, and the access required to deploy them in the most critical locations is constrained by the same treaty framework that governs everything else about Antarctica. The deep-time geology of Antarctica is still being assembled from fragments collected in the brief summers when the rock outcrops are accessible. The continent was not always where it is now. 400 million years ago, it was part of the supercontinent Gondwana, connected to South America, Africa, India, and Australia. The rocks of the Transantarctic Mountains contain fossils of freshwater fish, of early amphibians, of the same species of seed fern called Glossopteris that is found in rocks of the same age in South America, Africa, India, and Australia, the evidence that convinced scientists that the southern continents were once connected long before the theory of plate tectonics provided the mechanism to explain how they had separated. The Antarctic fossils were part of the original evidence base for continental drift. The question of climate change and Antarctica is inseparable from the question of what Antarctica contains. The ice sheet is both a record of past climate and a potential driver of future climate change. As the planet warms, the ice sheet loses mass through increased surface melting, through accelerated calving of icebergs from the glaciers that flow into the ocean, and through the melting of ice shelves from below by warming ocean water. That mass loss raises global sea levels, which threatens coastal populations around the world. The rate of that mass loss has been accelerating over the past 3 decades, as measured by satellite gravity sensors that can detect changes in the mass of the ice sheet from space. The acceleration is a matter of scientific consensus. The ultimate magnitude of the sea level rise that the ice sheet could contribute, and the time scale over which that rise might occur, remain among the most important and most contested questions in climate science. The human beings who have spent time in the deep interior of Antarctica describe an experience that is difficult to communicate to people who have not been there. The silence is total. At the interior research stations, far from the coast and from the ocean that moderates temperatures elsewhere, the wind can drop to 0 and the air becomes so still that the only sound is the sound of blood moving in the ears. The cold at those moments is a dry cold, unlike anything experienced in more temperate regions, a cold that does not feel wet or penetrating but that simply removes heat from the body at a rate that the body cannot compensate for without constant movement and insulation. The sky is extraordinary. At altitude, in the clear dry air of the Antarctic interior, the stars are visible during the brief polar nights with an intensity and clarity that observers describe as almost overwhelming. The absence of moisture, of dust, of atmospheric turbulence that blurs the sky in other parts of the world means that the stars of the Antarctic sky appear sharper and more numerous than anywhere else on Earth. The psychological effects of extended time in the Antarctic interior are well documented. The phenomenon called the third man factor, the sensation of an unseen presence accompanying the isolated traveler, has been reported by a significant number of Antarctic explorers and researchers who have spent extended time alone or in very small groups in the interior. The neurological basis of that phenomenon, which is also reported by climbers at altitude and by sailors in isolation, is not fully understood, but it appears to be related to the brain's pattern recognition systems generating a sense of presence in the absence of the normal social stimuli that those systems are calibrated to detect. The isolation of the Antarctic winter stations produces what researchers call the third quarter phenomenon, a period of psychological difficulty that occurs roughly 3/4 of the way through the winter isolation period, characterized by depression, interpersonal conflict, and a decline in cognitive performance. Studies of overwinter Antarctic crews have been used by space agencies, including NASA, to develop protocols for long-duration space missions, because the psychological challenges of the Antarctic winter station environment are the closest Earth-based analog to the psychological challenges of a long-duration mission to Mars. Antarctica prepares people for space not because it is cold, but because it is isolated, dark, confined, and psychologically demanding in ways that no other environment on Earth replicates. The people who study what lies beneath the Antarctic ice have to survive on its surface first. That is a constraint that no amount of remote sensing technology can eliminate. The role of Antarctica in the Earth's heat budget goes well beyond the simple reflection of sunlight from its white surface. The continent is the primary engine of the thermohaline circulation, the global system of ocean currents that distributes heat from the tropics to the poles and returns cold water from the depths to the surface. The thermohaline circulation is driven by the sinking of cold, dense, salty water produced when sea ice forms around the Antarctic coast, a process that releases fresh water into the ice and leaves the remaining seawater saltier and denser. That dense water sinks to the ocean floor and flows northward as Antarctic bottom water, the deepest and coldest layer of the world's oceans, which eventually surfaces in the North Atlantic and other regions after a journey that takes approximately 1,000 years. If the formation of Antarctic bottom water were disrupted by changes in the salinity or temperature of the Antarctic surface ocean, the effects on global climate would be profound and potentially rapid. There is a version of the Antarctica story that fits entirely within the framework of established science and international law, and that version is already extraordinary enough. The philosophical significance of Antarctica, as the last truly wild place on Earth, is something that the scientists who work there often reflect on but rarely write about in their technical publications. The continent represents a kind of negative space in human civilization, a place defined by what it lacks: human habitation, human industry, the noise and light and biological simplification that characterize everywhere else that human beings have touched. That negative space is not merely the absence of human influence. It is an active presence, a reminder that the natural world existed for billions of years before human beings appeared, and that it continues to operate according to its own logic in the few places where human influence has not yet reached. Antarctica is the last large region on Earth where the geological and biological processes that shaped the planet are still operating without significant human modification. That is what makes it extraordinary, and that is what will eventually make it impossible to leave alone. In that version, Antarctica is a continent of superlatives: the coldest, the highest, the most isolated, the most scientifically important. It contains the most complete record of Earth's climate history, locked in ice that extends back nearly 3 million years. It may harbor life forms that have been evolving in isolation for longer than the entire history of our species. It contains enough fresh water to raise global sea levels by 60 meters. It sits above geological structures of enormous scientific significance, including what may be the largest impact crater on Earth. And it is governed by a treaty that was remarkable when it was signed and that becomes more remarkable the longer it survives, because it requires the world's most powerful nations to agree, repeatedly and continuously, to leave the most resource-rich unexplored territory on the planet untouched. In that version, the reason no country is fully allowed to explore Antarctica is a combination of geopolitics, environmental protection, and the deliberately deferred question of mineral rights. The treaty works because it serves the interests of all its signatories better than any alternative. Open competition for Antarctic resources would trigger a geopolitical conflict that no nation wants. So the competition is suspended, the resources remain untouched, and the treaty continues by default. That explanation is rational and well supported by the historical record. It does not require any hidden knowledge, any concealed discovery, any classified science. It simply requires accepting that the world's most powerful nations agreed in 1959 to a legal framework that solved an immediate geopolitical problem by deferring a larger one to the future, and that they have continued to renew that deferral every time it has come up for review. The other version, the one that the anomalies and the classified documents and the premature ending of Operation High Jump suggest to some people, is less certain. It does not have the weight of the established record behind it. But it asks questions that the established record does not fully answer. What was in the portions of the Operation High Jump survey that were classified? What did the Soviet sonar detect in the Ross Sea in 1977? What is the true significance of the Wilkes Land gravitational anomaly? What was found in the accretion ice of Lake Vostok that prompted the Russian team to say the results were inconclusive and then publish very little further detail? Those questions may have perfectly ordinary answers. They may not. And tonight, that uncertainty is itself a kind of gift, a reminder that the most remote and most inaccessible place on Earth has not yet given up all of its secrets, and that the largest blank space on the modern map is not on the surface but beneath it. The question of what Antarctica looked like before it was covered in ice is answered, partially and provocatively, by the fossil record. When the first botanists accompanied the early Antarctic expeditions, they found coal seams in the Transantarctic Mountains, the compressed remains of ancient forests that grew on the continent when it was in a different climate zone. Subsequent paleontological work has recovered fossils of dinosaurs from Antarctica, including a member of the group that would eventually give rise to birds, recovered from rocks on the Antarctic Peninsula that date to the Cretaceous period. That Cretaceous Antarctica was not the frozen wasteland of today, but a forested, relatively temperate continent at high southern latitude, with a climate maintained by the warmth of a planet that had significantly higher carbon dioxide levels than today. The transition from that forested continent to the ice-covered one we know began approximately 34 million years ago, when the opening of the Drake Passage between Antarctica and South America allowed the Antarctic Circumpolar Current to form, isolating the continent thermally from the warmer ocean waters to the north. The future of Antarctica will be determined in the next 25 years, as the 2048 review of the Madrid Protocol approaches. The nations with the most to gain from opening Antarctica to mineral exploitation are already positioning themselves. China's expanding network of research stations is widely interpreted as an effort to establish scientific presence that could be converted into territorial influence when the legal landscape changes. Russia has never abandoned its interest in the petroleum potential of the Antarctic continental shelf. Several other nations have conducted detailed geological surveys that go well beyond what would be needed for purely scientific purposes. The ice shelves that fringe much of the Antarctic coastline, floating extensions of the ice sheet that extend over the ocean surface, have been collapsing at an accelerating rate since the late 20th century. The collapse of the Larsen B ice shelf in 2002, which disintegrated in a matter of weeks after being stable for at least 10,000 years, was one of the most dramatic single events in the recent history of Antarctic change. The collapse released approximately 3,200 square kilometers of ice into the Southern Ocean in less than a month, producing a flotilla of icebergs that persisted for years. The loss of the ice shelf removed a buttressing force that had been slowing the flow of the glaciers behind it, and the glaciers accelerated significantly in the years following the collapse, contributing to sea level rise at a rate that had not been predicted by models calibrated before the event. The environmental arguments for maintaining the prohibition are powerful. Antarctica is the last truly pristine large-scale environment on Earth. Its ice sheet plays a critical role in regulating global climate, both through its reflective surface, which bounces solar radiation back into space, and through the cold, dense water it produces, which drives the deep circulation of the world's oceans. Disrupting the ice sheet through mineral extraction activities could have consequences for global climate that would dwarf any economic benefit from the resources extracted. The counterarguments are also powerful. The minerals beneath the Antarctic ice include rare earth elements that are essential for the clean energy transition, for the manufacture of wind turbines, electric vehicles, and solar panels. The irony that the resources needed to prevent climate change may be locked beneath the continent that climate change most threatens is not lost on the policymakers who will have to navigate the 2048 review. The pressure to access those resources will be enormous, and the political will to resist that pressure will require a level of international cooperation that has rarely been achieved on any issue of comparable economic significance. The ice is also not static. The warming of the Antarctic Peninsula, which has been one of the fastest warming regions on Earth in recent decades, is already changing the surface of the continent. Ice shelves that have been stable for thousands of years are collapsing. Glaciers that were accelerating toward the ocean are moving faster than any model predicted. Species that had never been recorded on the Antarctic Peninsula are appearing as the climate warms. The Antarctica of 2048 will not be the Antarctica of 1991, when the Madrid Protocol was signed. It will be a continent in the early stages of a transformation whose ultimate extent is not known. What lies beneath the Antarctic ice will eventually be seen. The only questions are when, by whom, and under what circumstances. Tonight, for now, it remains sealed beneath 30 million years of ice, patient and cold and full of secrets that the world has not yet agreed to ask about openly. The sound of Antarctica is one of the least discussed but most distinctive aspects of the continent. In the interior, away from the wind and away from the ice-cracking sounds of the coastal zones, the silence is so complete that it becomes an experience in itself. Researchers who have spent time in that silence describe it as simultaneously peaceful and slightly menacing, a silence that the human auditory system, evolved in environments filled with biological sound, interprets as absence and therefore as potential danger. The wind, when it does blow, produces sounds on the guy wires and structural elements of the research stations that range from low moaning tones to high-pitched whistling, a natural Aeolian music that the station crews learn to read as a barometer of weather conditions. And the ice itself makes sounds, deep booming reports as it contracts in the extreme cold of the polar night, grinding and crackling as it shifts under pressure, occasionally a sharp explosive crack as a crevasse opens in a glacier. Tonight, as you prepare to sleep, the Antarctic continent is turning in the slow rotation of the Earth beneath a sky of extraordinary stars. At Vostok Station, a small team of Russian researchers is spending the polar winter in one of the most isolated places on Earth, sitting above a lake that has been liquid and sealed and dark for 15 million years. The instruments they maintain continue to record data from a place that no human being has ever directly seen. The lake below them is, as far as anyone knows, undisturbed. At the edges of the continent, the ice shelves are creaking under the pressure of their own weight and the warmth of the ocean water moving beneath them. Cracks that began in previous decades are extending slowly through ice that is hundreds of meters thick. The process is geological in its pace, but accelerating in ways that the ice itself records and that the satellites above record and that the researchers at a dozen national Antarctic programs monitor with increasing urgency. The experience of reading about Antarctica from a warm room, in the comfort of a bed or a chair, with the sounds of the inhabited world outside, creates a particular kind of cognitive distance from the reality of the place. Antarctica is not a metaphor or an abstraction. It is a physical place, as real as the floor beneath your feet, where the ice has been accumulating for 30 million years and where the silence is so complete that it becomes audible. The people who have been there describe the experience as clarifying. The irreducible reality of the cold and the silence and the absence of any human reference point strips away the noise of ordinary experience and leaves something that is difficult to describe but easy to recognize as important. Antarctica teaches you, in ways that no other environment can, how small the human world is relative to the world that contains it. The treaty that governs all of this expires, at least in its current form, in 2048. The nations that signed it have grandchildren who will be the ones to renegotiate it. Those grandchildren will inherit a warmer world, a world in which the resources beneath the Antarctic ice may look more necessary and more accessible than they do today. What they decide to do will determine what lies beneath the Antarctic ice means for humanity, and whether the extraordinary restraint that the original treaty represented can be maintained in a world that looks nothing like 1959. Antarctica is the last place on Earth that human beings have agreed, for now, to leave largely alone. That agreement is not permanent. It is not guaranteed. It is a political choice that is renewed, generation by generation, by the nations that have the power to make it. Understanding what is beneath the ice, and why it has been kept inaccessible, is part of the information that future generations will need to make that choice wisely. Antarctica is not a problem to be solved or a resource to be extracted. It is a mirror that the Earth holds up to the species that has, in geological terms, just arrived on its surface. What we see in that mirror depends on what we choose to look at: the science, the mystery, the politics, the ice. All of it is real. All of it matters. And all of it will still be there, patient and cold, long after the questions we are asking tonight have found their answers. Sleep now with that thought. The ice is still there. The lake is still sealed. The mountains that have never been seen are still beneath their covering, exactly as they have been for 30 million years. And the question of what lies beneath the Antarctic ice is still open, still patient, still waiting for an answer that no one has yet been given permission to find. That permission may come, or it may not. Either way, the ice does not care. It has been waiting for 30 million years. A few more decades are nothing to it. The medical research conducted at Antarctic stations has produced insights relevant to human health that would have been impossible to obtain anywhere else. The extreme isolation and confinement of the polar winter have made Antarctic crews the subjects of studies on everything from sleep deprivation to vitamin D deficiency to the physiological effects of prolonged darkness. The finding that Antarctic overwinter crews consistently develop elevated levels of certain inflammatory markers during the winter has prompted research into whether the immune system is affected by extended periods without social contact, a question with implications for the design of long-duration space missions and for understanding the health effects of social isolation more generally. Antarctica is, in this sense, a laboratory not just for Earth science but for human science. The international scientific stations of Antarctica are, from an architectural standpoint, some of the most extreme structures ever built. The need to withstand wind speeds of up to 300 kilometers per hour, temperatures of -80 degrees Celsius, and the slow movement of the ice sheet on which they sit has driven architectural innovation that has few parallels in conventional construction. Modern Antarctic stations are typically designed to be elevated above the ice surface to prevent burial by accumulating snow, to be modular so that components can be transported by aircraft and assembled on site, and to be capable of being relocated or dismantled when the ice beneath them moves beyond a safe operational position. The Concordia station, operated jointly by France and Italy at Dome C in East Antarctica, is entirely self-sufficient for energy, water, and air during the winter months, making it the closest terrestrial analog to a space station that currently exists on Earth. The data collected by Antarctic research programs feeds into models that affect decisions made by billions of people. The climate projections used by governments to plan infrastructure investments, by insurance companies to assess risk, and by international bodies to negotiate emissions agreements all rely on ice sheet models that are calibrated against Antarctic data. The accuracy of those projections depends on the quality and completeness of the data collected at Antarctic stations, and that data has gaps. The interior of the East Antarctic ice sheet is one of the least sampled large regions on Earth, and the behavior of the ice sheet in that region is one of the largest sources of uncertainty in long-term sea level projections. Every season of Antarctic fieldwork that expands the data coverage of that region reduces that uncertainty slightly, contributing directly to the quality of the decisions that humanity will have to make about climate change. The fauna that lives on and around Antarctica during the summer months are themselves adapted to extremes in ways that biologists have studied intensively. The emperor penguin, the only vertebrate that breeds on the Antarctic continent during the polar winter, has a set of physiological and behavioral adaptations that allow it to survive temperatures of -40 degrees Celsius and wind speeds of 140 kilometers per hour while incubating an egg on its feet. The penguin's huddling behavior, in which thousands of individuals pack together and rotate slowly from the cold exterior to the warm interior of the group, is one of the most sophisticated collective thermoregulation strategies in the animal kingdom. The mathematical modeling of penguin huddle dynamics, which treats the huddle as a self-organizing system of interacting agents, has produced insights applicable to crowd management, traffic flow, and the design of autonomous robotic swarms. The legal concept of the common heritage of mankind, which holds that certain resources belong not to any individual nation but to all of humanity, has been proposed as a potential framework for governing Antarctica after 2048. That concept, which was originally developed in the context of deep-sea mineral resources under the UN Convention on the Law of the Sea, would in principle prevent any nation from claiming exclusive rights to Antarctic resources and would require that any benefits derived from those resources be shared with all nations, including those without the technology or capital to access them directly. The practical obstacles to implementing that framework in Antarctica are enormous. But the concept has attracted support from smaller nations that have no ability to access Antarctic resources independently and that fear that the post-2048 legal landscape will be dominated by the nations with the largest Antarctic research presence. The midnight sun of the Antarctic summer, the period of continuous daylight that lasts for months at the South Pole, is one of the most disorienting aspects of the Antarctic environment for newcomers. The human circadian rhythm, calibrated over millions of years of evolution to the alternation of day and night, loses its reference point in the polar summer and must be maintained artificially through strict schedules and the use of blackout curtains over the windows of the sleeping quarters. The disruption of the circadian rhythm produces a range of physiological effects, including disturbed sleep, altered appetite, mood changes, and in some individuals a form of temporal disorientation that makes the passage of time feel strange and subjective. Researchers who have studied those effects compare them to the effects of long-haul transmeridian flights, with the difference that in Antarctica there is no recovery. The disruption continues for the entire summer season. The geopolitical significance of Antarctica is growing as the global competition for resources intensifies and as the effects of climate change make the continent's ice increasingly central to questions of coastal defense and sea level management. Nations that previously had no interest in Antarctica are now establishing research programs there, recognizing that presence in the treaty system gives them a voice in the post-2048 discussions that will determine whether the continent remains protected or whether it opens to exploitation. The entry of new nations into the Antarctic treaty system has changed its political dynamics, making the consensus required for decisions harder to achieve, but also making the treaty's legitimacy more broadly based. The question of what Antarctica means for humanity is no longer a question that a small club of wealthy nations can answer alone. The drilling of the Waist Divide ice core, completed by an American team in West Antarctica in 2011, produced a continuous climate record extending back 68,000 years with an annual resolution that allowed researchers to count individual years in the ice, much as one counts tree rings in wood. That annual resolution revealed the timing of abrupt climate events with a precision impossible in any other archive. The Younger Dryas cold period, the abrupt warming at the end of the last glaciation, and several other climate transitions could be dated to within a few decades of accuracy. Those precise dates allowed researchers to compare the Antarctic record with records from Greenland and from ocean sediment cores around the world, revealing the sequence in which different parts of the climate system responded to changes and providing crucial constraints for the climate models that project future change. The Antarctic petrel, the snow petrel, and the South Polar skua are among the only birds that breed on the Antarctic continent proper, as opposed to the subantarctic islands that surround it. The snow petrel is the most extreme. It nests in the nunataks of the interior, rocky peaks that protrude through the ice sheet, at distances of up to 400 kilometers from the coast, making it one of the most inland breeding birds on Earth. How the snow petrel navigates across featureless ice fields to find its nest sites, season after season, is not fully understood. The bird appears to use a combination of magnetic field sensing and olfactory cues, detecting the smell of the krill-rich ocean from hundreds of kilometers away and using that smell gradient to orient its return flight. The study of snow petrel navigation has contributed to the broader understanding of how birds navigate in polar regions where the usual landmarks of sun angle and star position are unreliable. The undersea topography around Antarctica, the shape of the seafloor that surrounds the continent, is as complex and varied as the subglacial topography beneath the ice. The Weddell Sea, to the south and west of the Antarctic Peninsula, is one of the deepest ocean basins on Earth, with depths exceeding 5,000 meters in its central portions. The seafloor of the Weddell Sea is covered in sediment that has been accumulating for millions of years, preserving a record of Antarctic ice sheet history that is complementary to the ice core record. Sediment cores drilled from the Weddell seafloor have recovered material dating back more than 30 million years, to the earliest formation of the Antarctic ice sheet, providing an independent check on the climate reconstructions derived from the ice cores and from the geological record on land. The lights of the Aurora Australis, the southern equivalent of the Northern Lights, are visible from Antarctic stations on clear polar nights throughout the winter. Caused by charged particles from the sun interacting with gases in the upper atmosphere, the aurora in the polar regions is more frequent and more intense than at lower latitudes, because the Earth's magnetic field concentrates the incoming particles near the poles. Researchers at Antarctic stations who observe the aurora routinely describe it as one of the most visually overwhelming experiences of their time on the continent. Curtains of green and red and sometimes purple light moving across the sky in patterns that are simultaneously structured and unpredictable, a display that continues for hours and that changes on timescales ranging from seconds to minutes. The study of the aurora from Antarctic stations contributes to space weather research, because the intensity and pattern of the aurora reflects conditions in the near-Earth space environment that affect satellite communications, power grids, and navigation systems. The legacy of the heroic age of Antarctic exploration, the period between roughly 1895 and 1917 when expeditions from a dozen nations competed to map and claim the continent, is preserved in huts, equipment, and personal effects that remain on the Antarctic Peninsula and on the subantarctic islands, frozen in time and protected by the dry cold that has prevented their decay. The huts of Scott and Shackleton on Ross Island, filled with the supplies and equipment of expeditions mounted more than a century ago, have been preserved by the Antarctic Heritage Trust and remain accessible to visitors. Walking through those huts, researchers and tourists who have made the expensive journey to the continent report a sense of temporal compression. The cans of food, the boots, the scientific instruments, the handwritten notes, all preserved by the cold as if their owners had left just recently, create a physical connection to the early 20th century that no museum or archive can replicate. The concept of Antarctic sovereignty is complicated by the fact that several nations have taken steps that imply the exercise of sovereignty without formally claiming it. Argentina and Chile have sent pregnant women to give birth on Antarctic territory, producing children who are technically Antarctic-born and who could serve as the basis for future citizenship arguments. Both nations have issued postage stamps featuring Antarctic territory. Both have named geographic features within their claimed sectors with names in their national languages and registered those names in national geographic databases. Those acts do not create legal sovereignty under international law, but they accumulate a kind of practical presence that could become relevant if the treaty framework were to dissolve and the question of Antarctic sovereignty were to be reopened under a different legal regime. The experience of returning to the inhabited world after a winter in Antarctica is described by those who have done it as a second culture shock, in some ways more disorienting than the original arrival at the station. The sensory richness of the ordinary world, the colors, the sounds, the smells, the density of human interaction, overwhelms people who have spent months in the sensory poverty of the polar interior. Trees, which Antarctic overwinterers have not seen for months, appear extraordinarily vivid and almost unreal. The noise of traffic, of conversation, of music, which the brain has been filtering for years and which it relearns to ignore, arrives with an intensity that requires deliberate cognitive effort to manage. Some researchers who have spent extended time at Antarctic stations report that they never fully return to the way they perceived the world before going. Something in the stripped-down clarity of the Antarctic experience changes permanently the way they register the complexity of the world they return to. The question of whether the Antarctic ice sheet has ever fully melted during the history of the Earth is one that the geological record has been slowly answering over the past 2 decades. Evidence from sediment cores drilled in the waters around Antarctica suggests that the ice sheet has been less stable in the past than was once thought. During certain warm periods of the Pliocene epoch, approximately 3 to 5 million years ago, when atmospheric carbon dioxide levels were similar to or only slightly higher than today, the Antarctic ice sheet appears to have been significantly smaller than it is now, and global sea levels were correspondingly higher. That finding, which has been reinforced by multiple independent lines of evidence, suggests that the threshold of ice sheet instability may be closer to current climate conditions than the models based on Pleistocene data alone would predict. The bacterial communities that have been found in the most extreme environments of Antarctica, including the dry valleys, The frozen lakes and the cryoconide holes on the surface of glaciers represent some of the most stress-tolerant life forms known to science. The dry valleys of Victoria Land, among the most arid places on Earth, support communities of cryptoendolithic microorganisms that live inside the translucent rock itself, sheltering from the extreme temperature swings and ultraviolet radiation of the surface while harvesting the small amount of sunlight that penetrates through the rock crystals. Those communities, which may grow only a few micrometers per year, are among the slowest living organisms on Earth, and they demonstrate that life can persist in environments where virtually every other organism would die within minutes. The warming of the Southern Ocean around Antarctica is proceeding faster than climate models predicted a decade ago, with consequences that are still being assessed. The circumpolar deep water, a mass of relatively warm ocean water that circulates around the continent at intermediate depths, is accessing the continental shelf in increasingly large quantities as the wind patterns that previously kept it offshore shift in response to ozone recovery and greenhouse warming. That warmer water is reaching the base of the ice shelves and the termini of the outlet glaciers that flow into the ocean, melting them from below and contributing to the acceleration of ice mass loss. The rate of that acceleration, and how it will evolve as the ocean continues to warm, is one of the most urgent and most uncertain questions in Earth system science. The acoustic monitoring of the Antarctic ice sheet, using seismometers placed on and in the ice, has revealed a world of sounds that the human ear would find alien if it could hear them. The groan of ice under pressure, the crack of new crevasses opening, the shudder of ice quakes as ice streams suddenly accelerate, and the deep subsonic hum of the entire ice sheet moving over its lubricated bed create a continuous acoustic signal that seismologists are learning to read. The icequakes of Antarctica, which are analogous to earthquakes but occur in ice rather than rock, can be detected by seismometers thousands of kilometers away, and their patterns reveal the internal dynamics of the ice sheet in ways that surface observations alone cannot capture. Listening to the ice is becoming one of the primary tools for understanding how the ice sheet is changing. The subantarctic islands that surround the Antarctic continent at latitudes between 40 and 60 degrees south are ecologically among the richest places on Earth, supporting enormous colonies of breeding seabirds and marine mammals that depend on the productivity of the Southern Ocean. South Georgia, a mountainous island in the South Atlantic roughly the size of Connecticut, hosts the largest concentration of wildlife in the Southern Hemisphere. Breeding colonies of king penguins numbered in the hundreds of thousands, fur seals in the millions, and wandering albatrosses with wingspans of 3.5 meters that raise single chicks over the course of a year-long breeding cycle. The island was the site of the most intensive phase of the whaling industry in the early 20th century, and the whale bone processing facilities from that period are still standing, rusting slowly in the subantarctic climate, as evidence of the scale of the exploitation that the Southern Ocean once sustained and that the current international agreements are designed to prevent from resuming. The discovery of ancient Antarctic forests in the coal seams of the Transantarctic Mountains is a recurring source of fascination for the researchers who work in that region. The coal, which formed from the compressed remains of trees that grew on the continent during the Permian and Triassic periods, contains fossil wood with the cellular structure of large trees, some with trunk diameters that indicate heights of 30 meters or more. Those trees grew at high southern latitudes, where the polar night would have deprived them of sunlight for months at a time, requiring physiological adaptations to prolonged darkness that are not found in any modern temperate tree. The fossil wood records the growth rings of those ancient trees, and the rings tell a story of alternating seasons, of growth in summer and dormancy in winter, at latitudes where the climate today would kill any tree within its first autumn. The connection between Antarctica and the rest of the world's climate systems is not a slow and distant one. It operates on timescales of decades and centuries that are directly relevant to the decisions being made today. The deep water that forms around Antarctica and sinks to the ocean floor carries dissolved carbon dioxide with it, sequestering that carbon in the deep ocean for centuries before it returns to the surface. That biological carbon pump, which depends on the productivity of the Southern Ocean and on the physical circulation driven by Antarctic cooling, absorbs a significant fraction of the carbon dioxide that human activities emit into the atmosphere each year. If the circulation that drives that pump were to weaken, as climate projections suggest it may, the atmospheric concentration of carbon dioxide would rise faster than current projections predict, accelerating the warming that is already disrupting the Antarctic environment. Antarctica is not a victim of climate change that exists separately from the systems that drive it. It is an active component of those systems. The debate within the scientific community about what level of access to the subglacial lakes is acceptable, and at what cost to the pristine environment those lakes represent, mirrors broader debates about the ethics of scientific investigation in sensitive ecosystems. The advocates for aggressive investigation argue that the potential scientific return, including possible evidence of a second independent origin of life or of life forms with biotechnological applications, justifies accepting some risk of contamination. The advocates for caution argue that the lakes have been isolated for millions of years and that any contamination, even partial, would be irreversible. Once the pristine environment of Lake Vostok is contaminated, there is no way to undo that contamination, and the scientific value of an uncontaminated lake is lost forever. That argument, between the value of knowledge and the value of preservation, is one of the most fundamental in the ethics of science, and Antarctica has made it concrete and urgent. The tourists who visit Antarctica, approximately 70,000 per year according to recent estimates, experience a version of the continent that is carefully managed and geographically limited. The Antarctic Peninsula and the subantarctic islands accessible by the cruise ships that bring the majority of visitors. That experience, which includes zodiac landings at penguin colonies and glacier walks and occasional encounters with humpback whales, is genuine and often transformative, but it is a partial picture of a continent whose interior is as inaccessible to tourists as it is to most scientists. The gap between the Antarctica that visitors see and the Antarctica that lies beneath and beyond it is itself one of the most distinctive features of the continent. It is a place where the accessible surface and the inaccessible interior are separated by barriers of ice, of cold, of distance, that even modern technology has not fully overcome. The future of the Antarctic Treaty System will be determined not just by the nations that currently participate in it, but by the nations that are currently developing the capacity to participate in it. As the cost of access to Antarctica decreases through advances in logistics and technology, and as the resources beneath the ice become more economically significant through the energy transition and the growing demand for rare earth elements, the number of nations with both the motivation and the capability to pursue Antarctic interests will grow. Managing the expansion of that stakeholder community within a treaty framework designed for a much smaller group of nations is one of the central governance challenges of the coming decades. The Antarctic Treaty was negotiated by 12 nations. Its current membership of 48 is already straining the consensus-based decision-making model on which it was founded. The question of water, fresh water, connects Antarctica to every person on Earth in a way that the continent's remoteness might otherwise obscure. The ice of Antarctica is the world's largest reservoir of fresh water, containing enough to supply every person alive today for a period measured in thousands of years. That water is currently locked in ice that has been accumulating for 30 million years. As the climate warms and the ice sheet loses mass, that fresh water enters the ocean and becomes seawater, unavailable for drinking or irrigation. The loss of Antarctic ice is therefore not just a matter of sea level rise. It is a matter of the depletion of a fresh water reserve that, while not currently accessible, represents a planetary-scale resource that will become increasingly relevant as fresh water scarcity intensifies in other regions of the world. The wind patterns of Antarctica, which drive the Antarctic circumpolar current and influence weather systems as far north as the temperate zones, are changing in response to both climate change and ozone recovery. The ozone hole that developed over Antarctica in the 1980s strengthened the westerly winds that encircle the continent, and as the ozone layer recovers, those winds are expected to weaken. At the same time, greenhouse warming is strengthening those same winds. The net effect of those competing influences on the wind patterns of the southern hemisphere is one of the more complex problems in climate science, with implications for the distribution of rainfall in southern South America, southern Africa, and southern Australia, all of which depend on weather systems that are influenced by the winds of the Southern Ocean. The research conducted at Antarctic stations has a time horizon that extends far beyond any individual career or even any individual generation of scientists. The ice cores that were drilled in the 1980s are still being analyzed in laboratories today, as new analytical techniques make it possible to extract information from them that was impossible to recover when they were first drilled. The samples collected by geologists working in the Transantarctic Mountains in the 1960s are still producing scientific papers, as new dating methods and new analytical frameworks reveal their significance in ways that the original collectors could not have anticipated. Antarctic research is, in this sense, an investment in a scientific commons that pays dividends across generations, a form of intellectual infrastructure whose full value cannot be assessed until long after the original investment is made. The subglacial topography of Antarctica, when visualized without its ice cover, reveals a continent that would be virtually unrecognizable from any map we currently use. The West Antarctic Basin, which contains most of the marine-based ice that is most vulnerable to rapid collapse, would be a shallow sea if the ice were removed. The Transantarctic Mountains would be a dramatic coastal range bordering that sea. East Antarctica would be a high plateau with mountain ranges rising from it. And the deep troughs that currently channel ice streams from the interior to the coast would become fjords. That imagined ice-free Antarctica, which researchers have reconstructed from radar data and glaciological modeling, is not a fantasy. It is a possible future state of the continent, one that could be reached over timescales ranging from centuries to millennia depending on how the climate evolves. The Antarctic night, experienced at the interior stations far from any source of artificial light beyond the station itself, is one of the darkest environments that human beings regularly inhabit on Earth. The absence of urban light pollution, the clarity of the cold, dry air, and the elevation of the stations above most of the atmospheric turbulence that blurs the sky at lower latitudes combine to produce a sky of extraordinary depth and richness. Researchers who have spent winters at Antarctic stations describe the experience of the polar night sky as one of the most consistently memorable aspects of their time on the continent. A sky that changes every night as the stars move in their slow circles around the celestial South Pole, that presents a view of the Milky Way and the Magellanic Clouds with a clarity that is rarely available anywhere else on Earth, and that creates a kind of enforced astronomical contemplation in people who might never otherwise think about the stars. There is a particular kind of rest that comes from contemplating something genuinely larger than yourself. Not the rest of distraction or entertainment, but the rest of perspective, the feeling that your own concerns, however real they are, exist within a context so vast that they cannot fill it. Antarctica provides that perspective more completely than almost any other subject. Tonight, let the ice do its work. Let the 30 million years of accumulated cold carry you toward sleep. The ice is patient. The mountains are waiting. The lake is dark and sealed and ancient. And you are very small and very brief and perfectly capable of resting. The last thing to carry with you tonight is this: of all the places on Earth that human beings have agreed to protect, Antarctica is the most complete protection and the most fragile agreement. It endures because every nation that could break it has calculated, so far, that it is not in their interest to do so. That calculation could change. The decisions that will determine whether it changes are being made right now by people who may or may not understand what they are deciding. Understanding what lies beneath the Antarctic ice is one of the preconditions for making those decisions well. That is why this story matters. That is why tonight matters. If this documentary kept you company tonight, subscribe to the channel. A new world to explore every week, always in the dark, always with time to think. and always with more questions than answers, because that is the only honest way to explore a universe this strange.